Hello everyone, I hope you are doing great. In two last videos, we talk about simulation of one-dimensional perovskite solar cell, and I hope you subscribe my channel in YouTube and leave your comments in the below of this tutorial videos and share me your opinion. Thank you. Okay. Here, as you can see, we have a one-dimensional perovskite solar cell uh, that we simulated before. Now I want to show you how we can convert this geometry to two-dimensional geometry and with easy way and very fast simulation. Okay, here I use the 2D axisymmetry and also 2D. It's depend on your opinion. Let us simulate 2D axisymmetric. 2D axisymmetric it allow us to convert our 2D geometry to 3D geometry also by symmetry in rotational direction. Okay. Here I right click on geometry 2. I use a rectangle and I must select width and height. I back to previous data. Here for 1D I use the ETL thickness from 0 to ETL thickness, and in the perovskite region I use ETL to perovskite thickness, and in the last section I use all of the thickness that we have used in the simulation. Okay, I use all of the thicknesses of material that we use in the simulation. ETL perovskite as the symbol of PVK, and HTL as whole transport layer. Let us use the height of all thickness and the width of arbitrary, for example 100 or 200 nanometer. Okay, I use build all objects. Here I can use the layers. By clicking this option you can choose your layers to specify each one of material. Okay, I copy the thickness of ETL here as layer 1. I build selected. As you can see, ETL will appear in this bottom of this geometry. I continue this form of writing. For layer 2 I use thickness PVK and I will select it. Okay, it's enough because the last one will difference between the remaining geometry from the ETL and PVK thickness. If you have n total plus, you have n minus 1 layer here. Okay, from union I build all, and you can see the final geometry. Okay, here we want to show you a simple way as I talk about peer reviews. I use semiconductor by right clicking and use copy option, and in component 2 I click right on the component 2 and use paste semiconductor. As you can see, the semiconductor will appear here, but the COMSOL say to you it must be a different name. As you can see, the label name here as semiconductor is semi, but here it's semiconductor semi 2. This option in the brackets, the function that you can do any operator on it. For example, integration uh, or some dividing or differences or any mathematic operation you needed. Okay, let us to introduce ETL. I click here as ETL. Trap assisted recombination for all of layer. I click all of layer here. HTL, the top of the geometry, and user defined generation for all of the layers. Also, I back to the um, semiconductor properties in 1D and get idea from the previous semiconductor. Okay, AU contact is it in adjacent of the HTL, and FTO contact is the adjacent of the ETL. Okay, FTO is here and AU contact is here. Okay. Okay, let us check all of the condition. Here we have Fermi-Dirac electron holes. Okay, the variables will appear here that will solve at the final of the simulation. Electric potential, electron and hole solution number variables. The material properties must be here. It's very simple. I click all of the materials and copy them, and I will paste them here by right clicking and paste multiple items. Okay, I rechecked that the domain of material is correct or not. Here is HTL is correct, PVK it is correct, and ETL it's okay and correct. Okay. Here I use the mesh. I can use this mesh that use a physics control mesh. For example, normal. You can choose a finer mesh and extra fine mesh for your simulation. It depends on your solution. Because you can multiple coupling the semiconductor physics by mathematical PDE, partial differential equation, or EWFT, microwave frequency physics for optical study. Here I choose semiconductor only as a one physics, and I use normal and I click the use for the physics control mesh. Okay, for a study we use a stationary study. As you can see, we have two semiconductor for solving. Here I don't want to compute semiconductor in 1D, as I show you semi for one dimensional and semi 2 it's defined for two axisymmetric dimensional. Okay, I just click the compute and I will wait for the results. Maybe in the, I don't know what will happen here. Maybe sometimes you choose a wrong mesh or wrong data, and the COMSOL will show you some errors. For example, maximum Newtonian iteration has been achieved, or some other errors, and you must recheck your mesh and your data. In most of case, the mesh is the main problem, that you must recheck that and use different mesh. It depends on your physics that you use in your simulations. Also, you can contact with me and I will respond you as soon as possible and solve your problem, and it's my pleasure. Okay, you can see here in the progress window the percentage of your progress and the parameter value. I used V app as applied voltage. You can see the values run. I can use a stop in each voltage that I want, but here I don't use this option because I want to run for all of the voltage that I introduce in the auxiliary sweep window. Okay, the convergence plot, it show you the the accuracy of your results. As you can see, our error is about 10 minus 11. It's very good for the accuracy of our results. Okay. Uh, for uh, for the future tutorial, I will show you how can we simulate 3D perovskite solar cell, and also adding some new equation to semiconductor equation, calculating the generation rate, recombination rate, and other physical properties of your simulation. Also in other topics such as cancer trophy, such as optical simulation of um, materials, I will provide some good tutorial videos, and I hope you enjoyed them, and subscribe my channel and leave your comments. Okay, we can also this graph is it's remained from previous simulation, and don't worry about it because the simulation are running for two-dimensional and it is not our concern. Okay, here I can choose semi that I01. It is not our case because, as I said, this must use the semi 2, or we can choose a study solution. I remove area and I use the semiconductor terminal for component 2. Okay, I use terminal. All of the variable you need, you can choose each one of them that you want. Here I use the semi 2i01. Okay, as you can see, the terminal current as the unit of ampere will appear here. I choose milliampere for the comparison with the other case. Okay. Also, we must choose our and define our geometry area here. As you can, maybe as you know, the two-dimensional axis symmetry has the cross section or area of the circle with the radius of this which it's mean the radius of the circle. Okay, I use the area of the circle P multiplied by width squared. Okay. We must choose correct brackets and all of necessary things. I use the units of milliampere per squared centimeter. Okay, and I plot it again. Okay, as you can see, let me to use manual axis, minimum x from 0 to 1.2 and the minimum from 0 to 22. Okay, as you can see, the terminal current milliampere square centimeter will appear here from 20 to 0, and the IV curve is correct, and you can use different data and use different IV. You can use parametric sweep for variabling and modifying some properties of material, for example band gap, density, and other things. Okay, to show you other two-dimensional physical properties, I use results 2D plot group. I click right and use surface. In expression, I can show any result that I want. For example, in electric, I use electric potential or electric field norm. Okay. For this data set, we must use a data set for 2D or use a solution. It depends on your, and your component must be a component 2. I use it. It will appear here, study 1, and for each arbitrary voltage, you can simulate electric field norm. Okay, as you can see, the electric field norm for different voltage will show here. Okay, and it depends on the voltage. By increasing the voltage, the electric field norm will increase significantly. Okay, for showing 3D schematic in your 2D simulation of axisymmetric, I use a revolution of 2D. I use a study 1, and I use plot. For each point that I want, you can choose your different point, and I can use the, let me show you the width and the height of the all devices, whole devices. For the Z, I can use 0 to Z, and also for the R direction, I can use nanometer, 200 nanometer. Okay, you can choose single value, 0 or 20. It depends on you, and also your resolution angle. It can be 270 degree to see what will happen between the layers. For the perfect geometry, you can it is hard to see what's happened inside these layers. Okay, in the results, I click right on it and use 3D plot group. In the 3D plot group, as the same, I use the surface, I use the revolution 2D, and in the expression I search in component 2 semiconductor, in electric current, each one of this data that you want. For example, I choose thermal diffusion current. I simulate it for you. Also, let me choose another data. For example, electric and electric field and electric in Z direction. Okay, as you can see, the electric field in the Z direction will appear and will show here. I can choose different voltage, and different results will shown here. Okay, thank you for joining us and showing this video. I hope you subscribe my channel. Please leave your comments, and if you need more videos, please leave a comment or contact with me via my email address or my WhatsApp numbers. I will provide any video about simulation of solar cell or something else. Don't worry, I work in different areas. For example, microwave therapy in medicine, laser therapy in medicine, and optical properties of materials, fluid properties of material, mechanics, and chemistry and plasma. Anything that you want, I will provide suitable video and tutorial for you, and I hope you enjoy that. Thank you. Take care. Have a good time.